So with this video we want to look at parallel circuits. A parallel circuit, it allows multiple pathways for current to flow. Multiple pathways for current flow. Essentially it's just multiple series circuits all running off of the same voltage source. So if I go back, take a basic 2-cell battery here, and we'll put a resistor in it, maybe a light bulb, and we'll say that's a 5 ohm resistor there, similar to what we used in the lab there. And when it's a parallel circuit, we'll simply add on to it another pathway with another resistor. Keep it simple right now. Right, so I have another pathway, and it's our 10 ohm resistor. So in the case of this first part right here, current can flow through the 5 ohm resistor, and also the current could flow down through the 10 ohm resistor. So we have multiple paths. If the 10 ohm resistor here were to break, this current flow, the red current flow we're showing here, wouldn't happen, but the 5 ohm resistor still works just fine. Right? There is no interference for that. Right? The same thing if I were to have something happen here in the 5 ohm, it would stop, but the 10 ohm would still have the current flowing through it. So that's the basic idea of the parallel circuit in terms of how it works. So if we go back and kind of look at the idea of the characteristics, right, of the parallel circuit, just like we did with series, characteristics of the parallel circuit, we'll start with the current. Right, so the current in this, if you look at it, we have current running through here and through here, so we're going to have to add up all the current. So the current, when we deal with that, is we say the current of the source provided by the source is simply going to be the sum of the current in each path. So maybe path 1 plus the current of path 2 plus however many more paths we have. We say path and not resistors because this path here we have one resistor in it, but it's possible we could have multiple resistors. There could be we could add in another resistor here and another resistor there, and so that total current based on what's going on in there, right, with this little series circuit would be what we would look at. So the current of the source is going to simply be the sum of all the currents in the various paths. So if we look at the information from the lab, went through and found in this 10 ohm resistor that there was a current of 1.8 amperes flowing through it, and in this 5 ohm resistor we had a current of 3.6 amperes, which, if you remember, was exactly the same as what we had when we had the 5 ohm by itself and when we had the 10 ohm by itself in part 2. So the sum of those two together then gives us the total current up here, which was 5.4 amperes. 5.4 amperes, like that. Alright, so that's kind of the idea of the current in here. Next, we want to look at the voltage. Alright, and with the voltage, essentially the source voltage is going to be the voltage you're going to find in each path. So path 1 equals the voltage in path 2 equals, just keep on going. And so in this lab, we went through this, we had an 18 volt source, and you should have measured approximately 18 volts here and another 18 volts here. And the reason this happens is because, again, this little pathway right here is a separate series circuit running off of the voltage source, and since there's only one bulb in it, all the voltage is in that one bulb there. The second path out here is connected independently, and so therefore it also has the 18 volts. Alright, Now, remember we talked about this with series circuits, that 18 volts was shared within that series. We had multiple resistors in here because the energy had to be conserved. We're not violating the law of conservation here. We're just running more electrical energy through in multiple paths, which is why, if you notice here, we have all this extra current. We have 5.4 amperes, whereas in our series circuit, we only had 1.2 amperes with these same exact bulbs in there. So again, the voltage on each path is going to be the same as the voltage in the source. And last, we look at the resistance in the circuit, and the resistance, total resistance, is going to be less. The total resistance is going to be less than the resistors that you have in here. It'll actually be less than the least resistor. Okay, so in this case we have a 5 ohm resistor here, so our total resistance is going to be less than that one. And this is true because there are multiple pathways. Since there's more places for the charge to flow, there's going to be less resistance overall. It's similar to having multiple hallways in our school. Right? Instead of everybody having to walk on one hallway, we can walk in multiple hallways. It'd be like traveling around in your neighborhood or in your community. You might have different ways that you can get to the same place. And if you have multiple ways to get there, then maybe you have less traffic overall because of that. Another thing that's important to look at, another example with resistance that I want to point out to you, is if we have a parallel circuit where we have a pair of equal resistors. Right, this is a special case here. So say I have a 10 ohm resistor here and a 10 ohm resistor here, and I want to know what the total resistance would be. I don't need to know anything about the voltage or the current or anything like that. The rule basically is for equal resistors. The basic rule for the equal resistors is that the total resistance is equal to 1/2 of one of those resistors. Alright, and this is true because the 2 here is dealing with the fact that there are 1, 2 pathways. So as long as they're equal resistors, we can look at this and say, alright, we'll just take 1/2 of that because it's equally splitting the current that would be flowing around, and therefore the resistance is going to be half of that. So in this case, the total resistance would be half of 10, which is 5 ohms. Right, and so that's the basics we're going to look at in terms of resistance for a parallel circuit. There's a little bit more to it, but for our purposes, this is all we're going to deal with in different examples that I would expect you to be able to solve. Certainly be able to tell that it's going to be smaller. Alright, total resistance will be smaller than any of the individual resistors. Your voltage source is going to be equal to the voltage on each path, and the current you have through the source here is going to be basically the sum of all the currents running through all the various series pathways that you have in the parallel circuit. So there's your parallel circuits, basic behaviors and characteristics. Alright, so we looked at the example of how we can go through every single branch and figure out the currents and add all those together to find the resistance. So we can also do this independent of the voltage. Makes it a lot simpler. You don't have to go through every single step. Since we're talking about parallel circuit where you have multiple pathways, that reduces the resistance. So the relationship between the total resistance and the individual resistors is an inverse relationship. So we have 1 over the total resistance equals the sum of 1 over each resistor. So let's look at this example over here. We just want to find 1 over the total resistance. We'll plug in the 1 over the 2 ohms plus 1 over the 3 ohms plus 1 over the 12 ohms. So we just simply taking the inverse of each of those. Alright, so now we need to add these together. So with fractions, we just need to have least common denominators on these, which would be 12 ohms. So if we put that down on the bottom of each of these, we're going to convert each of these so that it's in terms of over 12 ohms. So the first one, 2 ohms times 6, gave us the 12, so that goes on the top. And 3 times 4 gives us 12, so that goes on the top. And then the other one, last one there, just stays the same. So if we add all those together, we get 11 over 12 ohms. That is not the final answer, because remember, this is 1 over the total resistance. So 1 over the total resistance is 11 over 12 ohms. So all we need to do simply is take the reciprocal of this left side here, so that we end up with the total resistance over 1. And if we take the reciprocal of the left side, we need to take the reciprocal of the right side, and therefore we get 12 ohms over 11, and all that together then gives us 1.09 ohms. So we see very quickly that our rules from before are still true. The total resistance is less than the least of the resistors. And this is how we can do this. It doesn't matter what the voltage is. This allows us to figure out the total resistance of just any combination of resistors that we have in parallel.